Today I will talk about transient heat transfer, and then later in the day there will be a lecture on thermal stability analysis, which will be all about prediction of whether thermal runaway will occur in a lithium ion cell or not. And finally we will continue our ANSYS simulation tutorial that I had started yesterday. Okay, any questions or comments from the attendees at this point? All right, then let's get started. So we have seen that typically lithium ion cells come in two different configurations, cylindrical and prismatic. And the theme of our short course has been to understand the nature of heat transfer in these systems, ultimately to be able to keep lithium ion cells cool enough and prevent them from getting overheated, right? It turns out from a heat transfer point of view that if you look at the equations governing heat transfer in any system, for example, for a prismatic cell, we could write something like this. Solving this differential equation gives us the temperature field of the body, right? Therefore, we can say that the temperature field in the body is a function of K, rho and Cp. These are the three properties of the cell that determines how hot it will get, right? And therefore it is very important for us to know what the values of these properties are. Okay, so long time ago when I started my work in this field, this colleague of mine walks into my office and says, we have lithium ion cells, they're getting too hot, can you predict what we can do to keep them cool? And my first question to him was, well, what is the thermal conductivity of your cell? We went to the literature and found that there really wasn't a lot of reports of the values of these thermal properties, right? And therefore we and others in the community have spent a good amount of time and effort in measuring the thermal properties of these lithium ion cells. So today we will talk about how such properties can be measured or determined in order to guide our thermal design process. Okay, K is the thermal conductivity. We saw this when we were doing our introduction to fundamental heat transfer. If you may recall, it has units of watt per meter Kelvin. Cp is the heat capacity. That has units of joules per kg Kelvin. And rho is of course the density, that has units of kg per meter cube. What is the meaning of thermal conductivity? Thermal conductivity governs the rate at which heat flows, correct? Q double prime equals negative K delta T, correct? Or rather dt dx. For the same temperature gradient, material A and material B will have different flows of heat depending on their thermal conductivities, right? So clearly, if I want to remove heat out of this cell, its thermal conductivity is of paramount importance. This thermal conductivity for the cell should be as high as possible, right? That's the meaning of thermal conductivity. The meaning of density is of course quite clear. It is the mass density, how many kilograms there are per meter cube. The meaning of heat capacity, we have also seen this. The heat capacity appears in the expression for the energy content of the body. MCPT is the amount of energy contained in the body, right? And oftentimes the heat capacity basically determines how much energy is needed to raise the temperature of the body by 1 Kelvin, 1 kilogram of the body by 1 Kelvin, right? That is the classic definition of the heat capacity. Higher the heat capacity, greater is the ability of the body to absorb heat and keep it in it without any temperature rise, right? That is the reason why cities that are close to the ocean don't get very hot in the summers, because the ocean is able to absorb a great deal of heat from the sun without any temperature rise. Whereas a city in the desert with a lot of sand has low heat capacity, and therefore the energy coming from the sun will raise the temperature of the sand very rapidly, right? In the context of lithium-ion cells, we are interested in understanding what are the values of K, rho and Cp for the cells. Keep in mind also that while the heat capacity is just one single valued quantity, thermal conductivity may be anisotropic. So it is possible that I may have three different components of thermal conductivity, either kx, ky, kz, or kr, k theta, kz. In other words, for a given material, the thermal conductivity in the three directions may be different from each other. And we need to recognize that. Okay? I think it's important for us to get a feel for these numbers. What kind of numbers should we expect? What is a typical value for the density of any common material? What is the density of water, for example? About 1000, yes. So, for example, about 1000 kgs per meter cube is water. Typical metals is higher than that, plastics, polymers, etc. lower than that, gases even lower, right? So, for air, the density is of the order of only 1 kgs per meter cube. Okay? Somebody comes to you and says, I have a material with 100,000 kgs per meter cube. You need to say, slow down, something is not right. Yeah? A feel for numbers is extremely important. What about heat capacity? What is a typical number for heat capacity? Again, for water? Yes, the heat capacity for water is about 4184 joules per kg Kelvin. And this is actually one of the highest heat capacities of known materials. For metals, this is for water. For metals, it's of the order of 700 to 1000 joules per kg Kelvin. In other words, metals heat up faster. You don't need a lot of heat to raise the temperature of metal compared to water. As far as thermal conductivity is concerned, typical values, I think I've said it before as well, of the order of hundreds of watt per meter Kelvin for copper, and relatively low values for plastics, polymers, etc. Okay? In the context of these numbers, we would like to measure what the thermal conductivity of a lithium-ion cell is and place it in this range. Is it a good conductor of heat or is it a poor conductor of heat? And so on. Okay. Now, if I was to give you a piece of copper, it's a pure material, homogeneous material. It is expected to have the same thermal conductivity throughout, right? And it's just one material, it's just copper. But a lithium ion cell is not like that. We have already seen that a lithium ion cell comprises multiple layers of different materials, at least 5, right? Current collector, cathode, separator, anode, and current collector. So if you think of a cylindrical lithium ion cell that has a jelly roll of this sandwich of 5 materials, then the effective thermal conductivity of this heterogeneous material or heterogeneous body will be determined by the properties of the individual materials that make it up, right? If I am 30% muscles, 40% bones, and 50% blood or something like that, then my properties are determined by that proportion, right? How much of me is blood, what are the properties of the blood, and so on and so forth. Similarly, here, ultimately the thermal properties of the lithium ion cell effectively are governed by the properties of these individual materials. So let's talk about thermal conductivity first. And I also want to draw a prismatic cell in which, let's just consider a single layer cell containing 5 layers of these materials. Remember yesterday I said that this composite paper stack can be either folded into a prismatic cell or can be wound around into a cylindrical cell, right? I am interested in understanding what is the effective thermal conductivity of this stack, right? So if heat flows through this stack, what thermal conductivity will it see is the question being asked, okay? Let me define the coordinate system here. So let's say that this is the z direction and the other two are x and y. So z is out of plane, x and y are in plane. Yeah, is that okay? Yeah. We look at heat transfer from a thermal resistance point of view. So each of these layers is offering its own thermal resistance. And when we look at the flow of heat in the out of plane direction, z is the out of plane direction. Remember, this cell really looks like this. Sorry, wrong color. Sorry, wrong color again. This cell really looks like this, right? So z is the out of plane direction. In the out of plane direction, the resistances of each layer add up in series or parallel. Exactly, they add up in series. So I have resistance of the current collector, I have resistance of the cathode, resistance of the separator, resistance of the anode, and again resistance of the second current collector, 1 and 2, right? If I know the properties of each one of them, I should be able to find their resistances and add them up in series and find out the effective resistance. In other words, Ri, where I is the ith component, is given by Ti over A Ki. where T is the thickness of the ith component, K is the thermal conductivity of the ith component. Here I goes from 1 to 5. Question? Yes. Yes, we are talking about thermal resistance only. Correct, yes. Yeah, all of our discussion, unless I specify otherwise, R refers to thermal resistance, not electrical resistance. Okay. And so what is the total resistance? It is summation Ri. Correct? And this total resistance is given by total thickness divided by A times the effective thermal conductivity. So effectively the thermal conductivity is given by this expression, and therefore I can write T total over K effective, the A cancels out, is equal to summation Ti over Ki. Okay? Please feel free to ask questions at any point if something is not clear.
Every set will be behaved like a single cell, and it will be connected through the connector and have the common.
Sorry, I didn't understand the question.
Like we are having the prismatic cell.
Yes.
Does it like the spiral or single boiler paper which will be folded and put into the
Correct.
prismatic?
Yes.
Or otherwise, or it is like we are having a one cell, the connector and everything, another cell.
No. It's a continuous fold. It's a continuous fold. Do you know Maggie? If you take a packet of Maggie, the entire thing is one continuous string. Did you know that? In other words, if you are able to boil it very, very delicately, you should be able to stretch it out into one single noodle. Similarly, this prismatic cell is also one single fold. It's not multiple 5 packs arranged together. It's a single fold that goes round and round. Folding a cloth, exactly. Yes. Yes. So what happens is that each of these materials are manufactured separately. So you get one ream of current collector. These are very thin materials. You have another ream of anode, cathode, separator, etc. You bring all these reams together and press them together. Imagine take 5 papers of 5 different colors, put them together at high pressure. So you get one stack of 5 papers. You take that stack and you fold it to create a prismatic cell. Or if you take that stack and if you wind it around a mandrel in a cylindrical fashion, then you will get a cylindrical cell. Does that make sense? Cool. So here is a simple expression for the effective thermal conductivity of this cell. Keep in mind that this is the effective thermal conductivity in the Z direction. So I should call it Z. Now if the heat was to flow in the X direction, what would happen? These 5 resistances, how do they arrange themselves in the X direction? They act in parallel. They act in parallel, exactly. Yes. And therefore in the so this is all in the Z direction. In the X direction, things are slightly different. In the X direction, 1 over R total is equal to summation 1 over Ri. instead of this expression, now this is the parallel arrangement, right? Becomes a little more complicated, but nevertheless, from here, this gives me R total is L over AK, so K effective in the x direction over T total will be equal to summation Ki over Ti. Similar expressions, but slightly different. This shows, first of all, that the thermal conductivity of the cell is expected to be different in the out of plane direction and in the in plane direction. The lithium ion cell is expected to be anisotropic in nature. Sorry, yes? Okay. Additionally, I did not talk about this too much, but I would like to introduce also the concept of interfacial thermal contact resistance. What that means is that if I have two materials, let me use two different colors, that touch each other, the contact between the two is never perfect. Even if these are very smooth materials at the microscopic level, there's always some roughness. In other words, if I was to zoom in here, the actual contact region will look like this. So that the two materials are actually in practice touching each other, not over the entire area, but over a smaller fraction of the area. Because of this imperfect surface contact, there is always a resistance to the flow of heat across this material. Imagine in the worst case, if these two materials are barely touching each other, then heat will not be able to flow across. In other words, the interface will offer a very large resistance to the flow of heat. If on the other hand these materials are very, very smooth and they touch each other at 99.9% of the actual area, then heat will be able to flow very smoothly across the interface. What I'm saying is that at the interface of each of these materials, there will exist a contact resistance, which I will need to add here. The total resistance is not just the contributions of the individual materials, but also the contributions of each interface that occurs in this problem. We will look at that in more detail in a lecture tomorrow. But since we are talking about it here, I wanted to make an introduction to contact resistance. Okay? Let's go back to the question of measurement of thermal conductivity. So, how is K measured? If I give you a piece of copper, a thin sheet of copper or plastic or whatever, how do I measure thermal conductivity? Let's take this as an example. If I'm interested in measuring the thermal conductivity of this material, how do I measure it? Well, the thermal conductivity is governed by the fundamental equation Q equals negative K dt, Q double prime equals negative K dt dx, which in a one-dimensional problem could be simplified to Q equals negative K delta T over L and Ka delta T over L. In other words, if this is A, if the cross section area is A, and if the thickness is L, and if there is a temperature difference delta T across, and if that causes Q amount of heat to flow, then K is simply given by QL over A T1 minus T2. Right? So from an experimental measurement point of view, if I am interested in measuring the thermal conductivity of this body, I need to measure these 4 or 5 quantities. Which of these is the easiest to measure? No. Okay, it's easy to measure temperature, but it's much more difficult to measure temperature reliably. Okay, we have to think a little more about it. I think the easiest to measure is L and A. Right? You can measure the thickness of the body quite easily. Hopefully it is uniform, and you can measure the cross section area of the body. The challenge comes in measuring Q and the temperatures. So let's think about, as an experimentalist, how will I run this experiment? I give you this body. Where did that go? Here. Actually, this is a better example. Here is a sheet of copper or plastic. How do I run this experiment that we have in mind? It looks like this, right? So if I am just touching it, how much heat is flowing across it? Sure, yes. But let me answer this question. Let me ask this question first. Right now, how much heat is flowing through this body? 0. Why? Because the temperature is the same on both sides. Nothing is happening. So in order to force some heat to flow, I need to be able to impose a temperature gradient. If I can somehow maintain 30 degrees C on this side and 50 degrees C on this side, then some heat will begin to flow. And if I can measure how much heat is flowing, then I will be in business. Right? That's what I want to do. Or alternately, if I can force a certain amount of heat to flow across it and measure the temperature difference caused by that heat flow, then I'm good as well. You see what I'm saying? So in other words, in order to measure the thermal conductivity of this lithium ion cell, I need to hold it like this. I need to somehow make some heat flow through this and leave from the other side, and then figure out how hot does it get on the hot side compared to the cold side. Any ideas on how I can force some heat to flow across my cell? We can connect a heating plate, sure. So let's think about that. Here is my cell. What do you mean by a heating plate? So this is a metal plate perhaps. That generates heat. How does it generate heat? Sure. So it is connected to a power source, and there is some embedded heater inside it which produces heat. Okay. Then what is the next step in this experiment? What do we do next? We'll have to measure how much heat we are supplying. How will we measure that? Sure. So I can connect an ammeter and a voltmeter. Yeah, and V times I will give me how much joule heating occurs in this heater, right? Any objections to that?
We have to insulate this side also.
Sure. So the amount of heat that is generated in this heater is not necessarily the heat that passes through the cell, right? So in order to force the heat generated in this heater to go through the cell, I need to provide ample insulation. right? What kind of insulation should we provide and how much? There are all kinds of insulation, wool, tape, etc. available out there. It turns out we learned the hard way that it is nearly impossible to provide perfect insulation. Okay, some heat will nevertheless go away in one direction or the other. Okay, nevertheless, there are some things that we can do to minimize it. One simple thing we can do to minimize it is to take this entire experimental setup and put this in a big vacuum chamber. Because if there is vacuum all around, then there will be no convective heat transfer and conduction heat transfer would be minimized as well. Okay. Remember that there is no such thing as a perfect vacuum. There will always be some air left behind and there will always be some heat transfer occurring because of that air. Okay. Designing an experiment and running an experiment is a very humbling experience. Okay. On paper, you think you can do everything. Measuring it with a thermocouple is easy. It's not that easy. Okay. When you actually run experiments, and I know some of you do experiments in the lab, you know exactly how difficult it is, right? Blood, sweat and tears go into running experiments. All right. What is the next step? What do we do next? So we have some idea of this term now. A and L are easy to measure. We now need to measure the two temperatures, correct? Where do we measure those temperatures and how?
Of course, you can create a number of nodes, this side, number of thermocouples, one side, number of similar, other side. Have to take the approximate.
So where would you like me to place our thermocouples? Here?
On that surface, a number of
Multiple? Okay, sure. Each thermocouple comes with two wires, right? So you're asking to have a large number of wires. Each of these wires will need to go out of the vacuum chamber, right? So you need to make sure that you have space available to pull all of these wires out, right? Each of these wires will likely break the vacuum. You'll have to seal it up effectively and all that stuff. What about on the other side? On the other side, we also need thermocouples, probably, right? Should I place these thermocouples directly on the cell or directly on the heater? Or where should I place the cells? Sorry, the thermocouples. Directly on the cell or on the heater? Or doesn't matter? Sure, I think putting it directly on the cell makes a lot of sense because the heater, by the way, how will we make the heater touch the cell? Sorry? Sorry, I can't hear you too well. The example of iron. Okay. No, my question is, how do I stick the heater to the cell? Here is a cell. Here is my heater. Cell heater. Do I just leave it there? Or do I try to push it with some pressure, put a clip on it? There will always be some resistance between the two. We are trying to minimize it, right? What are some ways to minimize that contact resistance between the two? There are these materials called thermal pastes, thermal interface materials. They're like epoxy, high thermal conductivity epoxy. You put that paste here, it sort of acts like an adhesive, and then it's like a goop. You glue it down there, right? It will not eliminate thermal contact resistance, but it will minimize it. Okay. Having done all this, what do we do next? Okay, so I have a switch here. I start passing current, and then what?
Need to go
Wait, you're going too fast. You know, the difference between a PhD and the industry. In the industry, um, you go to your boss and say, here are these results. The boss says, you should have given me these results yesterday, right? Your PhD advisor says, you should be giving me these results tomorrow. You should be thinking more about it. Okay. In the industry, there is no time to think. They say, don't think. In academia, we say, think, don't do. Don't be in a hurry to do things. Okay. Come to think of it, all of this, once you have a plan, is very easy to do. Right? This is not rocket science. You're not trying to manufacture 5 nanometer silicon devices, right? Once you have all the equipment, the materials, once you have a plan in place, I'm sure you can put it together in a couple of days. You can get data out in other days, right? But I think the more important thing is to sit down and think about it. Okay? Think, don't do. Don't be in a hurry to do things. Because, for example, in this case, we forgot how we are going to measure the temperatures of the thermocouples. There are these maybe 10 thermocouples. How do you plan to measure the temperature of these thermocouples? So we need a proper data acquisition system to measure those temperatures. Hopefully you will use a software like LabVIEW and make a nice GUI, have nice little plots so that you are monitoring the temperatures of these cells, right? Now you go and switch this on. Suppose in your LabVIEW you have temperature plots coming out for you. What will you see as soon as you start passing current? The temperature will begin to rise, and then eventually it will reach a steady state, right? Hopefully you can see that there will be two sets of data. All these thermocouples will heat up a little bit, and they will all be quite close to each other, whereas this set of thermocouples will get much hotter. Correct? And it is this temperature difference that we are interested in. Yes? How will you determine exactly that temperature difference? How long are you going to wait to reach steady state? Huh?
that also has a challenge because ideally it will not, there will be some temperature rise.
Sure, yes, absolutely. Strictly speaking, theoretically speaking, steady state is reached at infinite time. You don't have infinite time on your hand. You have to graduate and go, right? Therefore, you have to figure out some other criteria to assume that, to be confident that you have more or less reached steady state. Typically, the criteria is to say that I do not want to see more than plus or minus some x degrees C fluctuation in temperature over y seconds. So if the temperature of a thermocouple does not change by more than 0.1 degrees Celsius over a 30-second interval, I will say that is my criteria to have reached steady state. So you can perhaps tell your LabVIEW code that look for this criteria. When this criteria is met, that is when I want to take my data. Right? Taking data is very easy, but you have to determine when and how to take your data. Right? Each of these thermocouples will also have some fluctuation and some spread within them. What are you going to do about those? Say you have 10 thermocouples on this side. What value of temperature will you obtain on this side? The average of those 10? Yeah? Is that reasonable? Sure, fair enough. Suppose one of them has a mind of their own. Suppose I have 9 of them nice and tight, and one of them for whatever reason is very different. What will you do about that? Replace it? Sure, yes. Replace it? Sure. It was a brand new thermocouple, so it was quite likely to work correctly, right? But anyway, let's replace it. Then what? Then if the new thermocouple also gives you this anomaly, then what would you do?
Then we will have to calibrate.
Sure, both are very good points. You have to go back and make sure that all of your thermocouples are calibrated. We didn't talk about this, but we should have been doing calibration even before we started this experiment, right? And to your point, we have to make sure that all of these thermocouples are attached correctly, there are no impurities or other problems like that, and so on and so forth. Contacts are perfect. We didn't talk about this as well. See, this is a can of worms. The more you talk about it, the more challenges you foresee in your experimental measurements, right? If you just walk into your lab and start running this measurement, good luck to you. You know, you will get a number for sure, but what kind of confidence do you have on that number? Nah. If I were your advisor, I would ask you to go back and think about it before you do it. Okay? Brings me to another question. How do I attach my thermocouple to the surface of the cell? Here is my surface. Let's go to a different sheet. Here is my cell. Here is my thermocouple. Oh, and by the way, we didn't even talk about what type of thermocouple. So if you go to, I don't know what is used here. We commonly use Omega. Omega is a well-known company. If you go to omega.com, the number of thermocouples they sell is what order? How many types of, how many different products of thermocouples can you buy from omega.com? 10, 100, 1000, 10,000? Probably 1000. So you have to choose among perhaps 1000 products. You can't say ek thermocouple dena bhaiya, right? That's not how it works. It's a little too complicated. They have too many applications, too many temperature ranges, too much sensitivity, etc. And you're standing there, imagine going to a grocery store and seeing 1000 different types of bananas, and you have to buy one banana. All you want is a banana, just give me a banana, right? But here you have to think very carefully about what thermocouple do you use. In fact, let me take a step back. Do you even use a thermocouple? Or is there something better is there a better technique for measuring temperature that would serve you well instead of a thermocouple? Sorry? IR camera, sure. So going back to the previous sheet, an IR camera has certain advantages. What is the key advantage of the IR camera? Yes, it is not in contact. You can measure it from a distance. So you can imagine that you can have an IR camera looking at it from here and be able to measure, right? The problem is you don't have optical access on this side, right? You have a heater on top of the cell, insulation on top of it, and you cannot possibly point your IR camera to the other side, right? Let's stick to thermocouples for a little bit. One more important question in a thermocouple is what is the size of the bead? So this bead size is also something that Omega will ask you. Do you want a 1 millimeter bead or do you want a 200 micron bead? The price is significantly different. The thinner your bead, the better your measurements are going to be, because the thermal mass of this bead plays an important role. You see, this thermocouple does not measure temperature instantaneously, right? The thermocouple that is in touch with my cell, once the cell gets hot, the bead of the thermocouple will get hot, and therefore a potential difference will be formed. This process does not occur instantaneously, and therefore the thinner the bead, the better it is. Oftentimes, people will take the pain of creating a little hole, like a little dent. Sorry, wrong color. In your body, so that you can place your thermocouple very nicely into this hole. You will probably put a lot of thermal paste around it and so on. Is that possible here in our measurement? No, I can't drill a hole in my cell, right? So that's out of the question. But nevertheless, I will want to put a good deal of thermal paste all around my thermocouple in order to make a good intimate thermal contact with the surface of interest. Okay? Now, having done all this, I take a measurement, I stick the numbers here, and I get a value, say K equals 0.65 watt per meter Kelvin. Actually, this is the funniest thing that happens with my students. I'll give you a simple example. Let's say K equals Q over delta T. Let me just simplify things for a little bit. I'm trying to make a point here. Suppose you measure Q and Q turns out to be 1 watt, or just say 1, okay? And suppose delta T turns out to be 3. This is from my measurement, okay? What is the value of K? Point what? Where do you want me to stop? Where do I stop? 2 or 3? 3. Why? That's rather arbitrary, right? Suppose for example, suppose the measurement accuracy of this thermocouple was plus or minus 1 degrees C. What that means is that the 3 degrees C temperature that you measured could very well have been 2 or could very well have been 4, anywhere between that rather broad range. If it was actually 2, then your thermal conductivity would have ended up being 0.5, correct? If on the other hand your delta T was 4, then your thermal conductivity would end up being 0.25. Now here is the point. Based on your measurement, the only confidence that you have is that my thermal conductivity is somewhere between 0.25 and 0.50 watt per meter Kelvin, whereas you are proposing that I report a thermal conductivity of 0.333. That is a little too exact, given how much uncertainty I have in my measurement anyway, right? So how you report your measured value should be consistent with how much confidence you have in the certainty of your measurement. If you go back, purchase more expensive thermocouples which are accurate up to 0.1 degrees Celsius, then your thermal conductivity will be between 1 over 2.9 and 1 over 3.1. Correct? I don't know what these numbers turn out to be, but this is much tighter now, right? And you should be confident of reporting thermal conductivity to the second or the third decimal. In fact, there is a whole field called uncertainty analysis, which I will not go into in this short course. But the idea there is exactly what we are talking about here, that if I carry out a measurement, suppose Z equals X over Y, and suppose there is a certain uncertainty associated with the measurement of X and a certain uncertainty associated with the measurement of Y, then what is the resulting uncertainty in the measurement of Z? no measurement is exact, right? In addition to measuring my thermal conductivity, I also need to understand what is the spread on it. It's not just 0.33, but it is 0.33 plus or minus something watt per meter Kelvin. Reporting the uncertainty along with the actual measurement shows that I am grounded, that I understand that my measurements are not perfect, right? According to the Hindu philosophy, there are 4 types of people in this world. Those who know that they know, okay? Those are the perfect ones. The second category is those who know that they do not know. If you are not in the first category, then at least you should be in the second category. That you should know that you do not know this exactly, right? And by the way, the fourth category is people who do not know that they do not know. They are the ones usually who shout the most and speak the loudest and attract a lot of attention, okay? Don't be that type. Either be number one, you know that you know, the perfect people, right? Or you should know that you do not know. So figuring out the uncertainty in your measurement is almost as important as carrying out the measurement itself. And so you've got to have a plan for that as well, right? The other thing is repeatability is also important. Meaning that you carry out this measurement, get a value, and you go home or go away to your hostels, come back the next day, repeat the same, exact same measurement again. Do this 3 times and see where your numbers are. If you get a value of 0.5 today and 0.7 tomorrow and 0.3 the next day, something is not right, right? Things should not fluctuate as much. What else can I do in terms of repeatability that will give me confidence in my measurements? So what I proposed just now was to go back, come back the next day and measure the thermal conductivity again. What else could you do to give me some more confidence that I'm doing things right? Sure, absolutely. So this heater that is passing current and producing heat is the thing that is driving the flow of heat. What if I double my current, start producing more heat? If I do that, then I expect that my temperature difference, if the heat flux goes up by 2 times, how should the temperature difference change? See, from this equation, K should be a constant, right? So if Q goes up by 2 times, T1 minus T2 should also go up by twice, right? So you should verify that. That's an excellent suggestion, right? At some point in time, if you start passing too much current through it, then the temperature rise will be so high that the thermal conductivity, which in principle is a function of temperature, will begin to show its temperature dependence, right? We are trying to run this measurement at room temperature. Strictly speaking, the temperature difference should be extremely small so that I am measuring the thermal conductivity exactly at room temperature, right? In other words, I need to provide just a small puff of heat and measure the small temperature difference that occurs as a result of that. I'll never be able to do that, right? I need some substantial amount of heat to get a good measurement. But that amount of heating should not be so large that this temperature difference becomes so high that the thermal conductivity of the cell, its temperature dependence begins to appear in my measurements. But nevertheless, increasing or decreasing it by a little bit and measuring the resulting temperature difference will give me confidence in my measurement. Right? In your PhD defense, if you show one set of data and then say, you know what, I measured it slightly differently as well, and the numbers are very similar to each other, that gives your committee a world of confidence that you didn't just wake up one morning and do a measurement. You actually did it systematically and so in a systematic manner, right? One more thing that I would do here, in addition to repeating this experiment, is to prepare 5 specimens of the exact same cell and measure thermal conductivities of 5 identical cells. Okay, and these cells need to be purchased in the same batch, right? You don't want to do this repeatability measurement on one cell that I purchased today and another cell that was lying in the lab for 1 year, was probably leaking a little bit, right? That's not what you want to do. 5 identical samples should give you relatively similar thermal conductivities. Does that make sense? Any questions? Yes, it is possible to do that. So the simplest way to do that from an experimental point of view, did you mean experimentally or experimentally? Yes. So from an experimental point of view, suppose I have 2 materials, a red material and a green material that touch each other. The question being asked is there some way for me to measure the contact resistance between these 2 bodies? The simplest way to do it is to basically run the same measurement on that sandwich. So I will take a heater on this side and I will embed a number of thermocouples along the length of, along the thicknesses of both materials. In other words, I will drill a hole and place a thermocouple here, 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 and one as close as I can to the mating surface. And I'll do the same thing on the other side as well. Okay? And I'll do the same thing, you know, insulation, vacuum, blah, 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 the whole shebang. In a setup like this, in steady state, if I was to plot the temperatures reported by these thermocouples, T versus Z, let's say, and let me use red color for the thermocouples on this side and green for the others, what should I expect to see? This thermocouple will be the hottest, right? And then this, and then this, and then this, and then this, right? What about the green thermocouples? The slope will change. The first thing is that the slope will change. What is the meaning of the slope? What does the slope represent? Thermal conductivity, right? So if these 2 materials have different thermal conductivities, then the slopes of these measured data will be different. So you might see something like this. More importantly, for our purposes, if this is where the intersection is, and if I was to extrapolate this data and that data as well, we will find that there is a small temperature difference at the interface. You see, if these 2 materials had perfect contact between them, there would be no temperature difference at the interface. That delta T would be 0. That delta T represents contact resistance, and you can determine contact resistance simply as this delta T divided by Q, the amount of heat that flows across. Did I answer your question? Compared to? Yes, yes, absolutely. There will be more uncertainty here. That said, you know, most experiments, even on measuring thermal conductivity, are not done on a single material. Even if I am only interested in measuring the thermal conductivity of the cell, I will probably want to have an arrangement like this, where this is my cell and this is some other standard material, perhaps quartz. Why? Because the thermal conductivity of the quartz is well known. If I measure the slope of, of the temperature profile in the quartz, what will that give me? Q quartz is equal to K quartz times delta T quartz divided by L quartz, which means that by placing a standard material next to the cell, I am able to measure the heat that flows through the quartz, right? But it is reasonable to assume that the heat flowing through the quartz is equal to the heat flowing through the cell, right? So by placing a standard material, I am able to indirectly measure amount of heat that flows through the cell. And a bonus of this measurement is the contact resistance. This measurement also tells me the contact resistance. Why is it important, or why is it useful for me to have this standard material? Because remember that we said that the amount of heat that flows through the cell is given by I square R, right? But that is a very crude approximation, because the amount of heat that is generated in the heater, not all of it goes through the cell. Some of it might go through the insulation, some of it might leak here and there, and therefore I really wish to determine exactly the amount of heat that flows through the cell, not the amount of heat that is generated in the heater, because the two may be different from each other. And this is one way of measuring directly the amount of heat that flows through the cell. By doing this, I no longer have to depend on current and voltage measurements to know the amount of heat that flows through. Yes?
We are making a perfect context, and how we will place our thermocouple at the interface of each material.
That's a good point. We are not placing thermocouples at the exact interface between the two materials. We are trying to get pretty darn close, right? But at the end of the day, we are going to extrapolate this curve and meet the two curves at the intersection. Even if I had, say, just a few thermocouples, sorry for the inconsistent color, even if I had just a few thermocouples, I would still have, if this is my interface, I can always make straight lines and get my delta T, right? One more benefit of doing all this extra hard work is that I will get this data. Let me right? This data will never be perfectly linear, right? So imagine two scenarios. One scenario is where I get data like this. The other scenario is where my data looks like this, right? What does this tell me? A and B. This is experiment A and this is experiment B. What does this tell me? A versus B. Which measurement would I trust more? Why A? Yes, absolutely. You see, from heat transfer theory, we expected all of this to be valid only in the case of 1D heat transfer. And when I have one-dimensional heat transfer, the temperature distribution is a straight line, theoretically speaking, right? If my measurement also gives me a straight line with very good variance, right, then that gives me confidence in my measurements. If on the other hand I find that my data looks like this, then what this is telling me is that heat is entering the body but it is leaking away somewhere along the way. It's not all going in a straight line. If it was to go strictly in a straight line, then the temperature drop will be linear and you will get a tight fit here. But here it tells me that something is not right with either my measurement setup, my thermocouples, or something. I have to go back to the drawing board and figure it out. Does that make sense? Yes, question?
Previous slide, when we are talking about the battery, so we can measure the
This one?
where you consider it as a battery, and here we are measuring the thermal conductivity in X direction. We have to measure in Y direction just by seeing any one of the interface or any one of the connection we can measure.
No. In order to see, in this case, the way I have designed my experiment, the heat will flow only in this direction. Correct? It is being produced here uniformly. So the only way for it to go, and there is insulation on the top and bottom, the only way for it to go is in this direction. If I want to measure thermal conductivity in the other direction, I have to flip it over and apply heat on the Y face and force it to go along the Y direction. Right? So if I am interested in measuring the three components of thermal conductivity, X, Y, Z, I wrote that somewhere, right? X, Y, Z, then that requires three separate measurements. Okay? Oh, and measuring R, theta, measuring thermal conductivity for a cylindrical cell is even more fun, and it's even more, it throws up a lot more questions. Okay? The last thing that I want to comment here is that there are a couple more things that I can do to tighten my measurements, to ensure that I'm doing everything right. One is that, look, this heat that is produced in the heater passes through the cell, passes through the quartz, and then is removed by the air, right? If instead of it being removed simply by the air, I have like a cold plate, which is cooled by water, then by measuring the flow rate of the water and the inlet and outlet temperatures, m dot Cp delta T of the water tells me how much heat is being picked up by the water, right? So on one hand I have heat generated by the heater, on the other hand I have heat removed by the water. Did I say water? Heater. Heat generated by the heater, this is heat removed by the water, and finally from here I also have the heat passing through the quartz. I am measuring the same quantity three different ways in order to gain confidence in my measurements, right? And this three-way check can be very helpful. Suppose, I'll give you a simple example. Suppose we find this is heater, quartz, and water. Suppose through our measurements we find that 10 watts of heat enters, right? I'm just giving some numbers here. This is 9.8 and this is 9.7. Do these numbers look reasonable? Any burning problems from these numbers? Let me give you one more data set for comparison. Suppose this is 10 watts, this is 10.1 watts, and this is 10.2 watts. Is there some problem with the second set of data? Yeah. You see, in this measurement, I have 10 watts of heat coming in. How can 10.1 watts of heat pass through the quartz unless there is some other heat source, which there is not, right? I'm not heating up this cell any other, this system any other way. Maybe if I'm running these measurements outside on a hot day, that can perhaps explain this data. In which case, you should go inside and run this experiment away from the sun. But in a regular experiment, you cannot. It is unlikely that you'll have more heat passing through the quartz than was generated in the heater, or more heat picked up by the water than was generated in the heater. Right? This gives you yet another layer of confidence around your measurements. You see, whenever you measure something and present it to people, you have to convince them that your data is right. It's very easy to take a measurement. If you're in a hurry, I can run this measurement within a day. Right? But I would much rather that you think about it for a week and then take the measurement. Take another week. Take your time. But provide enough evidence to be able to prove your case. It's almost like going to the court and trying to prove somebody is guilty of murder. Look, I have this evidence, I have this CCTV footage, I have these people saying that they saw him, and so on. Right? Similarly, I have 3 different pieces of evidence confirming and giving me confidence in my measurement. Then if I say that I have measured the thermal conductivity of the cell to be 0.5 watt per meter Kelvin plus or minus 0.2 watt per meter Kelvin, people will say, yes, I think you're right. We have reasonable confidence in your measurements. Okay? Any questions or comments? Yes, we have measured contact resistance, and we will talk about it probably tomorrow. We have a lecture on interfacial contact resistance, interfacial thermal transport. So we will do that tomorrow morning. Okay, very interesting topic, and we'll be glad to look into it in a lot of detail. Any other questions here? So I think this is a good discussion, and what I would like to propose is that the next lecture, which was nominally on thermal modeling, I want to modify that a little bit, and I would like to spend part of it to continue our discussion of experimental measurements, if that is all right with everyone. Yes, because my main intention actually was to discuss measurement of thermal properties of a cylindrical cell. And I'm almost out of time. This is also as interesting as measuring thermal properties of a prismatic cell. It's a little more challenging, in fact, right? In the case of a prismatic cell, I had 2 faces of the cell at which I could place thermocouples and measure temperatures and determine thermal conductivity. What do I do here? If I am interested in measuring the radial thermal conductivity, according to Fourier's law, QR equals negative KR del T del R, right? So, if I want to run a measurement on a cylinder similar to the prismatic cell, then I would have to place my thermocouples at 2 radial locations, and I would have to force the heat to flow in the radial direction, and that will give me the value of KR. Now tell me, where do I place my thermocouples here? Here is my cylinder. Let me show you the top view. This is the center of the cylinder. What is the easiest location for me to stick a thermocouple? On the outer surface. Absolutely. So here I place one thermocouple. Where do I place the second thermocouple? No, there is no point of placing a thermocouple on the opposite direction. That doesn't help me, because these 2 thermocouples are both at R equals R. Right? In order to measure the radial thermal conductivity, I want the heat to flow in the radial direction, inwards or outwards. And I want to measure the temperature at 2 R locations. Both of these represent the same R location, R equals capital R, right? Where do I go and place my second thermocouple? Sorry? In the center? Sure. I can drill a hole in the cell and place a thermocouple in the center. The problem with that is that if I drill a hole in the cell, the volatile electrolyte in the cell will evaporate and it's not really a cell anymore, right? This lithium ion cell is a hermetically sealed system. I cannot possibly drill holes in. If this was a copper cylinder, sure, absolutely, that is exactly what they would do. You would drill a thin hole, put a thermocouple in the center. In fact, you'll place multiple thermocouples here, here, here and there. But that I cannot do with a lithium ion cell. The only radial location that I have available, unfortunately, is the outer surface. This was indeed the challenge that Stephen Drake and I were looking at in 2013 or so. So this other professor I keep talking about walks in, says, here is my cell, can you tell me how hot it will get? I said, okay, do you know its thermal conductivity? He said, what is thermal conductivity? I said, okay. I look at the literature, there were no reports of thermal conductivity of a cylindrical lithium ion cell. So we said, we've got to measure it. And then we were staring at it and wondering, what do I do? Our first thought was also to put a thermocouple in the center, but David Wetz, this other professor, shot it down saying, no, you can't drill a hole in the cell. That's not allowed, right? So we had to come up with a new technique for measuring the radial thermal conductivity of a cylinder where we had access only to one point. Okay, we will talk about that in more detail in the next lecture. By the way, just a few finishing points before we take a break. In that measurement, we were also interested in measuring the axial thermal conductivity of the cell, because ultimately the interest is in determining if the two thermal conductivities are very different from each other or not. I hope you can see that measuring the axial thermal conductivity of this cell is not that difficult, right? It will in fact be very similar to this prismatic measurement that we've been talking about. So I can take the cylindrical cell, I can place a heater on one side, I can insulate the heck out of it, and I can measure the temperatures at the two axial ends of the cell, right? Along the axial direction, I do have easy access to place thermocouples at the two ends. So measuring the axial thermal conductivity is relatively easier. Measuring the radial thermal conductivity is a lot more challenging. And measuring the circumferential thermal conductivity, kill me, I can't do it. Okay, measuring the axial thermal conductivity of a body is super challenging. My students and I have tried it and we've given up on it for now. It's one of my things to do before I retire, I hope. Okay, yes. No, not at all.
But let's say if I do care
Yes,
and I want to measure the heat,
yes,
so I somehow select a 2D problem. I don't know which 2D problem.
yes,
I design some kind of 2D problem.
yes,
For this the solution I know.
yes, exactly,
Here and
exactly, yes.
then I notice the temperature of the boundary.
And
rather than try to make it 1D problem, I actually solve a 2D problem.
correct.
I go here and I try to solve.
Sure, yes. That is roughly the approach we took as well. The problem we ran in was not on the theory side. On the theory side, I can formulate a 2D problem and I can solve it, and I can figure out what to expect. But the problem we ran into was in order to replicate those conditions in a real life experiment. For example, in this case, in order to force two-dimensional flow of heat in the r and theta direction, I need to place a heater only along a certain circumference, right? I don't want to put it all around. And then where do I measure the temperature? Do I measure the temperature here? Sure, perhaps, right? There were too many experimental difficulties in making this happen the way the theory says it will happen. That's the short story, you know. How do I take a heater and I stick it only to a small section and not allow, you see, I have to insulate the rest of it, right? Part of it has to be heated, part of it has to be insulated, but inevitably some of this heat will leak in this manner, and all kinds of other logistical difficulties. We said, okay, you know, to solve this problem, we said, take my cylinder and put a screen and have a radiation lamp here, so that the heat, the radiative heat passes through this slit and only influences this part of it. But there the problem we ran into was we did not know how many watts of heat is reaching the surface of the cell. In the previous measurement, I square R through the heater tells us how much heat is generated. Here we had no idea. In fact, Swapnil, who was Dr. Tyagi's MTech student, was the one who ran these measurements, and you know, I gave him a very long rope, but it was an extremely difficult measurement, and ultimately we just had to move on and do something else. The other problem here, by the way, is that most materials do not have distinct values of Kr and K theta. Ideally, to run this measurement, you need very different values of Kr and K theta to be able to distinguish between the two. But we did not know where to go and find a material with strongly anisotropic values, which you know the values of. We know that a cell, a lithium ion cell, probably is anisotropic in that way, but we don't know its values to validate it, exactly. But then this is a chicken and egg problem. How will I ever validate it? Somebody else has already measured it, right, to be able to, for me to validate it. But then if somebody else has already measured it, then why am I doing it? Right? So all kinds of problems and challenges. We are past our time, so I'll stop here and we'll start exactly here where I'll talk about some measurements using cylindrical lithium ion cells. Alright, so let's take a good 30-minute break. We'll restart at 11:30.